Hello everybody. So this is the Q&A part that goes with Hello everybody. So this is the Q&A session that went with the session 1 of the YouTube video. So for all those of you that watch, I appreciate it. Thank you very much. And today I'm rocking the SharkFest 14 t-shirt. This is actually my favorite t-shirt, and that's why it looks so all worn out, because this is the most comfortable and I happen to like this one the most. So anyway, I figured I'll try to bring out every t-shirt of SharkFest that I have. Okay, so let's get right to the questions. So, by the way, not for nothing, let me turn on my picture-in-picture here. Okay, so before we start, not for nothing, not one of you mentioned my Oscar-worthy performance of imitating Taken. Not one comment. So I took that very personally, and so just know that, okay? Now, let's go to the questions, and before we do, take a look at the screen here. Let me zoom in. So in the future, whenever you have a question and you're posting a question to whatever video, when we get to the packet trace part, always use the @ symbol here that you see, so that whatever question you ask, reference the timeline in the video so I can quickly jump to it and figure it out. Because keep in mind, some of these traces I may not have looked for a couple of years. So if you just randomly say, hey, why didn't the client do XYZ? I have to go digging through all of that to answer that question. So the more you help me, the faster I can answer, or more likely it is for me to answer the question. Okay, so don't forget, make sure you use the @ symbol followed by the time mark, and by commenting like that, I can jump right to that question. Okay, so let's go to the questions. The first 3 questions are kind of all related, right? So Ramesh, Datacom guy, and Himesh asked the same thing about why would adding buffers cause issues, right? The more the merrier. Shouldn't it be the more the merrier? If I have a lot of buffers, shouldn't that help? And I actually did this session last night, by the way, and it would have been a Synax Sunday video, but I didn't quite like the audio quality, and to prove that to you, here's the diagram that I drew last night. But let's go back to the drawing board here. Let me zoom in and get situated and talk about why buffers, infinite buffers, are a bad thing, in fact, okay? So we talked about our pipe here, and then we had the servers here, and we have the PC or the client here, right? When you think about TCP, one of the things that a textbook answer for TCP is that it's a streaming protocol, or it's streams oriented, not streaming, streams oriented. What that means is there is no beginning and end to TCP. Sure, there's a synsinac, finfinac, setup and teardown. Those are control things. Once the data starts flowing, it can stay on for 500 years. It can stay on for 2 seconds. There is no end of file delimiter in TCP, right? There is no end of file marker that you might see in documents. So keep in mind that it's nothing but just bytes of data as dictated by the application to shuttle across to the other side. So a good analogy is to think about water. So let's say that we have here, and I'm going to attempt to draw a spigot here. That's a horrible spigot. I suck at Pictionary, by the way, as you might imagine. So let's say we have water that's coming out of here, and the water is in fact exactly the same as TCP. Okay, and so when those packets fly from the server to the client, packet number 1, 2, 3, 4, 5, and 6, etc., and it's flying in this direction, think of that as water filling up this pipe. And this pipe represents, you got it, bandwidth. Okay. When that pipe is full, whether it's water or data, then remember the client says stop. And we'll talk about in just a second how it sends that stop signal. So this is why we have to have a receive buffer, right? Because the data is going to come in hot and heavy much faster than application can handle. So this is the receive buffer. Then the sender also has a buffer, but it's not so much for performance reason. It's to guarantee delivery, because remember this packet that we sent flying? Those get replicated here automatically by TCP in the event that this packet number 4 goes missing, or really the data that's in packet number 4 can be reconstituted and sent out here as a retransmission. Okay, and that's why this is the send buffer. So the buffers are slightly different in terms of function. All right, so why is it that we have all this buffer, and why can it impact performance? Because when you use it, you're actually lying to TCP. TCP is feedback oriented. When there's packet loss, there's congestion control that kicks in and says, oh, I better slow down. This is like driving on a highway and you see brake lights up ahead. We automatically start downshifting, right? Or at least slowing down and tapping on the brakes so that we don't run into that car. And this is what TCP does. Every packet that it goes out, whether it's through timestamping or packet loss feedback, it says, oh, I better simmer down or I can ramp up. And that's a congestion control that we'll hit further down the road. So let's talk about, from my water example, how buffers can hurt the performance as opposed to helping that performance. So now we're going to create a new pipe here. Okay, same thing. The data is going to go in here, except this time, and assume that the send buffer exists for this guy as well. Okay. On this side, though, instead of a buffer, what I'm going to do is I'm going to build a giant well. Okay. And why did I do that? Because this, let's see here. Okay, that's better. So this well is a draining point. So as the water or data comes filling in, it actually doesn't fill, right? Because you have water always seeks the lowest level, and water starts filling here. This is the receive buffer. This is what it's doing. So what's going on while this well is getting filled? This pipe isn't getting full. There's no feedback telling the sender to slow down. Okay? No one is sending that because I have this ginormous tank that's absorbing all this water. Okay? So why is that a bad thing? Because what if the buffer has to be discarded for any number of reasons? Okay? That means that you have all of this buffer's worth of data that can get lost, and now TCP has to scramble to make up for this, right? Because remember, there's a corresponding send tank that has to keep track of every drop of water or data. Okay, so it's very expensive in terms of memory space in trying to keep track of all this data as the sender and as the receiver. Okay, because by the time this water fills up and then the pipe fills up, it's too late. You're way over the capacity of this bandwidth. Okay, in our case, I called it a pipe, but really it's a circuit, Ethernet connection, MPLS, whatever that transmission medium might be. By the time the water fills up here, all of this has filled up too, and the recovery from that can be extremely painful. And we'll actually see some of these use cases as we get into advanced packet analysis later. So hopefully that answered that question. There was another question here, and it was from, let's see, Pramod here, saying that a server is reporting packet drops, and why would that, or how do you know, how can you start to troubleshoot because the server is reporting it? So one quick way to do that is to look at some netstat statistics. Oops, I already had it copied. And all you have to do is netstat-ptcp. So give me the network statistics for the protocol TCP, broken down by, and you can see here that there is UDP, TCP, ICMP, there's IGMP statistics, IPv6 statistics. There's quite a few statistics. So let's go ahead and filter that and just say, find the word packets in this output. And the ones that I care about are the received packets discarded. So you can see here, I actually have some packets discarded. So what does it mean to have packets discarded? So if you actually look at Microsoft documentation, it says that, I'll zoom in, any number of reasons. For example, packet could be dropped to free up buffer space. Exactly what we talked about in my little water pipe diagram, right? And this is why having, again, this, coincidentally, this is a good question because it reinforces that packets in fact can and do get lost even inside the buffer. Okay. There is, however, a big hint that you can use to see if the client is under duress. So the question is, whoever is dropping the receive packet, okay? In this case, I'm going to say, for sake of argument, that the client is the one that's dropping packets. Seemingly, we don't know. Is there some tip or hints that Packet Trace Wireshark can tell us that in fact that's the case? Okay, is this client not able to keep up with the onslaught of data coming from the server? So let's go to, and in fact the answer is yes. And one of the ways to do that is to look at this window size. This is a TCP window size, which is the receive buffer that we talked about. Okay, so this is the one on the left side of the diagram that I drew, the receive. Remember, the send buffer, send window size is never exposed inside of a packet. And you might think, well, Hansung, how did you get this TCP window size? Because in mine, it doesn't have that. It might look something like this. It might have the colorization rule turned on. I have it turned off. And the way to do that is take any TCP data or packet and go down, open up TCP transmission section, and then go down to the window size here. You can also use calculated window size, but we'll get into the details of that when we get into how to set up Wireshark later. For now, I'm going to just use the window size value and say apply as a column. And that gives us a column here. And the good thing about this is I can actually sort it based on this. So if I click on the header, I now have a ascending sort where the window size is going up. Okay. Except something is happening here, and it's not the problem that I described. Okay, which is the client having a problem? Remember, the receiver sends the receive window size of how much I, as the receiver, can hold on to that packet. Okay, and believe it or not, this whole time I was actually gesturing to the camera because I thought the picture-in-picture was turned on. So all that, again, Academy-worthy acting wasted. So I'm being facetious, of course. So that's kind of my sense of humor. So take a look at this. The receive window size here is from the server perspective and not the client. So how do we change this so we can get an accurate picture of, is the client under duress? Can the client keep up with what the server is sending? And all we need to do is just use IP source 192.168.1.10 in this case. And let's take a look. So now I'm looking at the advertised window space of what the client. So this is basically the client saying, hey, you can give me 64K more. Oops, you gave me some here. Oh, no, this is Cincinnati, so be careful. Cincinnati, so two different window sizes. And why didn't it take my filter? Okay, there we go. So now notice here that this is all 192.168, and you can see the window size going up and down, up and down, up and down. So let's pause here for a second. Okay, so we started out at 64K. Could be bigger depending on whether window scaling is on or not. But again, we'll tackle that later. So for now, just play along at 64K window size. And we got some data, clearly, because my window size went down, meaning I received data, and then I received data. So I need to keep advertising a smaller well size, smaller receive buffer size. So these are people filling up data, filling up my waiting space, right? That doctor's lobby that I talked about in the first session. And the application is not really picking this up. between the packets up here that we saw where it started at 64K. So this whole time from where we saw it earlier to here, the receive buffer was not drained. Okay, and then you see here, oh, I'm gonna update my TCP window size, and oh, by the way, I caught up, and I now emptied out my buffer, and you're good to go. Okay, so when you're troubleshooting packet loss, you should see a corresponding decrease of window size before you actually discard those packets, because once the window size is full, you're going to discard whatever comes next to it. So you might say, wait a minute, Hansang, you said that there's a mechanism to stop this packet, right? And in fact, there's a stop sign that the client can send to the server to say stop, and that's called window size 0. And you can see here that the TCP window size is in fact 0. Okay, and I can open it up and show it to you. Window size is 0. Okay, and you see here I'm sending another duplicate, window size of 0, duplicate, window size of 0. So what is mechanism here? This is keep alive. This is Windows probing. So what the server is doing, this 10.server in this particular trace file is doing, is looking at the server is waiting and saying, hey, you haven't updated me in a while. Are you still there? Is your window open yet? And sends the packet, and 100 milliseconds later, the client says, stop, window size 0. Okay, that's what that stop sign is. And then 60 seconds later, the client says, or the server says, hey, you still there? And he has to send, remember, he has to retransmit at least 1 byte, because without data, the receiver never really replies, right? There's no acknowledgement coming unless you send it some data. So the client again says, nope, not ready. The server sends the same byte again and again. That's why these show up as duplicates. All TCP window probing are in fact textbook definition of retransmission, because you're retransmitting the same data. There's no sense in retransmitting an entire block of data. So you just transmit 1 byte, and the window size says, nah, can't handle it, can't handle it, can't handle it, can't handle it, etc. So the tip for finding out whether the client or the server is receiving the packets and you're dropping it because the application cannot keep up is to keep an eye out on that window size. If the window size goes down, that's okay. That's Windows receive buffer doing its job. But the minute it hits window size 0, now you know that the buffer is full and the application cannot pick up and empty that buffer fast enough. Okay, so hopefully that was a clue that you can investigate. And then finally, there was another question on the bandwidth. Okay, and I guess I didn't copy it down here, but there was a link given. Oh, sorry, let's go to this camera here. And a Cisco link on packets per second, and how do you calculate the bandwidth? So believe it or not, this can be as elementary as take all the packets and divide by unit of time, and you'll get a wildly inaccurate bandwidth report. Because when you average, you lose granularity. Okay, and in fact, textbook answer-wise, well, maybe not textbook, mathematically speaking, the only true answer to what is your bandwidth or utilization is 0 and 100%, because either the packet's on the wire or it's not. There's never where a packet is only half on the wire. Okay, Ethernet works by utilizing the entire bandwidth at that instant, and then the packet gets sent, and then somebody else gets a shot at it. Okay, so really, mathematically it's 0, 100, but clearly useless. We can't use it. So what do? We average that number over time, and that's why it gets a little bit dicey. Most SNMP tools, when you're polling, for example, Cisco interfaces can go down to 30 seconds. The newer ones can go down to 5 seconds, where every 5 seconds you measure how much data you sent or saw, and you average over 5-second buckets. Okay, so you're averaging over 5 seconds. Other interfaces, the shortest interval you can do, SNMP interval, is 30 seconds or even 1 minute. And it's very taxing to keep track of all those because remember, routers are not really general purpose compute. Their job is to be taking packets from one side to the other side, not calculating these things. So be careful, keep an eye on your CPU utilization. And but regardless, this is why calculating bandwidth is difficult. So someone always asks me, well, should it be 5 seconds? Is there a best rule of thumb? And my rule of thumb is I go to 1 minute and then I go to 1 second. So I actually like to use 1 second to see what the peak would be. However, if I were still designing trading floors, I may not use 1 second granularity. I may use 10 millisecond granularity. Okay, 1 millisecond or even nanosecond, you might have some of those of you in the financials that says, hey, trading, I'm in trading, nanoseconds matter, and I want nanosecond granularity report. And you'll see why in just a second why that's kind of meaningless when you get down to the nanoseconds. All right, so when you calculate Ethernet, there's some discrepancy on what's the Ethernet size. Is it 1500? Is it 1518? Is it 1514? Is it 1538? What is it? And why is there a discrepancy? And that's because Ethernet, when it first came out, needed to do some house cleaning. Okay, so we have a gap time, interframe gap time, the IFG, so that in between transmission of packets, Ethernet frames, the network card has to do update registers, update counters, all those things that we saw, packet drops and all of that happens during the interframe gap time. Then because of historical reasons, there's a Ethernet type or length and also CRC. However, CRC, IFG, interframe gap time, and preambles of the world are handled by the FEE, the network card. So the operating system really doesn't have anything to do with it. So you're not going to see those because that happens at the electrical level of the network card. So a lot of times those are not calculated. However, if you want to be truly accurate, you want to include those full, because on the wire itself, you're going to see that. Now the question is, if I have a sniffer on a span port, why don't I see those? Because again, the switches are getting rid of some of those because they are handling the IFG and sending the packet and not necessarily the full thing. Okay, network taps, you'll be able to see it on switches. Things that quote unquote process the packet and send it to you, give you a copy, tend not to do that. Again, with a caveat of it's vendor dependent. Okay, so that's the question on bandwidth. The kind of the tangent, kissing cousin to bandwidth is a serialization delay. So what is a serialization delay? Let's go to my handy dandy tape here. The serialization delay is here's my pipe again. And this time, instead of water, we're going to use a car analogy. Okay. And what I'm going to create are these toll booths that are packets here that are lined up. What these are TCP session. So this could be some dub. This is telnet. This is SSH. And this is, I don't know, SSH. Another SSH session. Okay, tuples, conversations. So this is your traffic at the top here. But what happens is there are many more of these applications than there are toll booths. And each one of these packets have to go through here to get a shot. So this is a 1-lane tunnel. Okay, so even though there are multiple lanes here, there's only really one lane for the tunnel here. So what happens? Well, you get queued up. You have to wait your turn. Okay, so when, for example, when these packets get drained out, maybe it's because of quality of service, etc., then you get to go next. Okay? Again, this is a simplistic answer, but I'm simplifying it for the sake of argument or ease of explanation. Okay, so the serialization delay is how fast can I move the traffic from here to here? Okay, how fast can I do that? Remember, I can do that at 1 bit at a time, right? Because it's bits per second. And That's where the serialization delay comes in. So even though there are multiple lanes here on this side, okay, you have multiple lanes here, there's only one lane inside this tunnel. So you get queued up, okay? So you get stuck behind this traffic jam and you have to wait your turn, and the switch uses the built-in buffer, inbound buffer, queues you up, and then drains you out when the opening here at the tunnel happens. And that is actually just a function of the speed of the interface you're using. So I use 1250 byte packet, the full packet, including IFG and everything else, because remember at the electrical level, we have to account for all of that. And that comes out to 10,000 bits because there's an 8-to-1 difference between bytes and bits. And let's use this one first here. This is a T1. If you guys remember T1s, it's laughable now, right? Because I have a gigabit service at home, but this used to be the thing to have back in the days. So T1 is 1.544 megabits. E1 in Europe was 2.0 megabits per second. Again, 1250 bytes, same data sent across at 1.544 megabits per second comes out to 193,000 bytes per second. And in order for you to serialize that, send it across, is 6.4 milliseconds, as you can see there. Okay, and so I just, to make it easier, I put the millisecond in red and microsecond in the green. Okay? But if we go to 100 megabits per second, then it's way faster to get across because the serialization delay is only 1 micro. Okay, you can see 100 microseconds. Then with 10 gigabit, it's 1 microsecond. And as you get, and I just said earlier, well, when you get to nanoseconds, it's really not pertinent unless you know your fiber runs. You need to actually account for the length of the fiber that the server is using, and because it's that fast, right? And if you don't know how long your fiber patch cable is, or even the fiber patch cable to your sniffer, then you're going to get incorrect answer. Okay, because remember, I'll just draw it up here real quick. Remember how we how we capture packets. When we have the server on this side, and we have the client or PC on this side, there's a switch port, and then we have a span port here, don't we? And the sniffer sits over here. You need to know the fiber patch cable here. You need to know the fiber patch cable here because you need to know the total flight time across that fiber patch. But when you send this packet via span port to the sniffer, this time gets added, right? Because I don't see that, depending on the direction, I'm only seeing the delay here, which may be very different than delay that you see here and here. So this is why I'm saying at 10, people want nanosecond granularity, you had better measured out your patch cables to be that accurate. Okay, that's it. I believe I answered all the questions, so I'll go ahead and process this and upload it today. And we'll have a video coming later this week where we pick up on the concept of buffers and performance once again. Okay, we'll dig into it a little bit deeper. Suggestions are welcome, so if you have any topics for future episodes, let me know via LinkedIn or on the YouTube comments, and obviously with questions, don't forget the @ so that I know where to jump to. Okay, take care, guys.